Shown in the figure below is the ChairSwing ride from an amusement park. The ride operates by rotating around the vertical axis, causing the chairs to swing outward at an angle of 40 degrees. Determine all of the following. A. The radius of the circle made by the swinging chair. B. The tension in the 3-meter long cord. And C. The velocity of the chair. Those who are familiar with this ride at an amusement park will recognize that this chair, for example, swings towards you, around to the other side, and then behind the pole, making a circle. The radius of that circle is given by a line connecting the person in the chair to the center of the circle located over here. We can use geometry to find the radius of the circle. This portion is 4 meters as labeled, and the entire radius of the circle will be 4 meters plus x, where x is this side of the following triangle. We recognize that x is the side which is opposite to the 40-degree angle. Therefore, we use the sine function to determine that x will be equal to 3 meters times the sine of 40, which gives us 1.93 meters. Since the radius of the circle is 4 meters longer than x, we find that r will be equal to 5.93 meters. Circular motion problems are force problems, and the first step in every force problem is to draw a free body diagram. I'll draw the diagram for the moment when the chair is on the right, as shown here. In this case, when we name each force acting on the chair, we first think of gravity, which is mass times g in the downward direction. And second, we notice that the chair has been tied to a string, or a chain in this case, so that a tension pulls along the string. That's it, gravity and the tension. There is not an additional force known as the centripetal force, since centripetal is merely a direction. For this two-dimensional free body diagram, we orient the coordinate system by the usual principle, with the acceleration. Since this object is moving in a circle, we recognize that even though its speed is constant, it is accelerating, and the direction of that acceleration is toward the center. So the plus direction will be to the left and will be labeled as the centripetal direction. To complete our two-dimensional coordinate system, we need another coordinate which is perpendicular to this, and we'll name that one as vertical. To solve this problem, will simply require us to write one force equation in the centripetal direction and another force equation in the vertical direction. These two will yield the answers that we seek. Let's begin with the centripetal. The only force making a contribution in the centripetal direction is the tension. However, the tension is not entirely directed in the centripetal direction. For this reason, we'll need to take components of the tension. To do so, we begin by following one axis, and we continue until such time as completing the triangle for the tension is done in parallel to the other axis. We now need to get our 40-degree angle placed inside of here. We recognize by the principle of alternate interior angles that if this angle is 40 degrees, so is that one. So the component of the tension in the centripetal direction is the side opposite to the 40-degree angle. Therefore, tension times the sine of 40 is the only force in the centripetal direction. As always, we sum forces and set that sum equal to mass times acceleration. So we ask ourselves a question. Is there an acceleration in the centripetal direction? The answer to that question is always yes. The amount of the acceleration in the centripetal direction is v squared divided by the radius of the circle around which we're rotating. Although in this equation we do know the mass is 80 and the radius is 5.93 meters, we don't know the tension and we don't know the velocity. Therefore, we place a box around this equation, save it for later, and continue on with the analysis of our free body diagram. The other direction in the free body diagram is the vertical. We haven't labeled a plus direction in the vertical because there is no acceleration along the vertical coordinate. We'll choose up since that seems natural and recognize that the tension has one of its components, the side adjacent to the 40 degrees in the vertical direction, and the gravity force is in the minus vertical direction. The sum of the forces is always m times a, and since the chair is spinning in a horizontal circle, there is no acceleration in the vertical direction, so this sums to 0. This equation has only one unknown, the tension. Plugging in the numbers, we find a tension of 1,023 newtons. This tension can then be used in the centripetal equation to solve for our final unknown, which is the velocity with which the chair is moving, yielding the numerical result 6.98 meter per second.